Hello, and welcome to Ants Are Everywhere. Today, we're going to look at stable diffusion. Now, this was a fan request. I'm not entirely sure what the best way to think about the stable diffusion source code is. We will look at the repository on GitHub, but there's a real sense in which stable diffusion is actually about model weights rather than source code. So we'll start by looking at the source code, and then if we want to know more, we may pull up some papers or take a look at one of the UIs to see how, in practice, something like stable diffusion works with all of its components. Before we get there, I want to just mention briefly. I had mentioned on Monday that I was starting a fund for funding open source development. I want to say a couple of words about that. First of all, the idea is that this will be an endowment or a perpetual fund, similar to some of the endowments you see for colleges or universities. And the idea is you invest some money in forever, in perpetuity, and the power of compound interest will build that sum of money up over time, similarly to when Benjamin Franklin gave, I don't know, something like $100 or some amount of money to Philadelphia and somewhere else. And over like a century, the compound interest allowed them to like build large buildings with what was a very modest sum. So we're going to do the same sort of thing. As I mentioned on Monday, the way the organization that will control the endowment will be a religious organization. I'm reviving the ancient Pythagorean religion. So I just wanted to say a quick few things about how I'm thinking about that. This will be a naturalistic religion. No like spooky sky people or anything like that. We don't know a ton about the original Pythagoreans, but I put together what I think are the core of the beliefs based on the little bit that we know, and they are roughly these: that the universe is governed by mathematics. The way that the Pythagoreans originally put it is by number. So theirs was a very much number theory driven world. But at the same time, they proved a lot of things geometrically. And it's believed, I think, essentially that they discovered geometric proof. So I think the right way to interpret what they were up to is that there's an order to the universe. It's mathematical. It respects equations rather than being governed by like bearded mountain people, the way that the Olympians, the worshippers of the Olympians thought. Also, the universe is characterized by harmony. You can also think of this as symmetry, that if you just have a chaotic universe where everything is fighting against each other, then you don't have eventually life forms, you have just chaos. And so there is order, symmetry, harmony, and those things are why there are things like organisms that can kind of fight against the march of entropy. Very important, music is governed by mathematics, namely music theory, and it should be used to change your mood and whatnot. And we shouldn't hurt animals. This was a big part of the ancient Pythagoreans. I think we should have some it was so fundamental to what they were up to that I think we need to take it seriously. And finally, there was an inclusion of women that was very forward thinking for their time, and they participated as equals. And there are known theorems of ancient female Pythagoreans who proved things. So they were doing mathematics as well. And also, I made this little logo. So the way that the endowment's going to work is I'm going to put it in a it's going to be managed by a separate organization, the way that sort of colleges do. So Harvard has some kind of hedge fund arm that manages its endowment, similarly with Yale and Princeton. Here's the little logo mock-up that the AI's made. So I think I'm going to flesh this out. It's going to be called Thales' Holy Hedge Fund, which I think is a pretty good working title. And it will have a golden olive press and I couldn't get the AIs to write the whole thing, but I think this font is more or less cool. So I'll play around with that. And as of now, we have about $100 in the fund. And so if we follow the normal endowment rules of withdrawing about 5% annually, that's only a few bucks. It's easy to compute 5% because you just, if you have a like 10 to the K, you 10% is 10 to the K minus 1, you just take half of that. So we'll need to build that up, but that's where we're starting. Hello, kerning, coming. Let me pop this out. Is this saying? I think this is coming maybe as a joke about kerning, but I'm not sure. If I've misunderstood you, let me know. All right, so let's take a look at the stable diffusion. This is old. Look, this is 2 years old, 3 years old. And I think that's a sign that this is probably not really the right place to be. We can look at other branches to see if there's anything more recent. No branches. So I think that this is where it is. And so we'll look at it. We'll see what they're up to. And then probably we'll look at, like I mentioned, maybe the automatic, whatever it's called. There's like 6 ones in there. One of the UIs, or we'll see if we can find like a maybe the stable diffusion paper. I'm assuming that there's some paper. We have a README, and here I guess is the paper. It's a latent text image diffusion model, thanks to a generous compute donation from Stability AI. All right, and so I don't know what Lion is. This is the original one. It's 512 by 512 images. I know like Stable Diffusion XL or something I think it's called is like, I believe 1024 by 1024. And I think there's also a Stable Diffusion 3. I don't know what that's up to. You need Conda, which is some Python package to manage Python environments because Python environments are so terrible. And then we have a bunch of weight files. I guess we could try to read one of the weight files. This one is the smallest one, I guess, 256 by 256. And maybe we should look at what Lion is. A large-scale artificial intelligence open network. Truly open AI, 100% nonprofit. It provides datasets, tools, and models to liberate machine learning research. Okay, I'll have to look at this later. So this is, I think, something about maybe datasets primarily. Lion, I'm going to call it Lion. I don't know what else to call it. And 400M is an open dataset containing 400 million English image text pairs. So this is, I guess, just labeled images. And so this is one of the things that they trained on. What is it? This is the paper? All right. Okay, and we got some graphs. Here are some examples of images that are generated. I'm sure somewhere there's also the prompts. Maybe the prompts are embedded in the image somewhere. But I'm not going to do that. Okay, so that's an overview. Let's look at this. We have data. That might be relevant to training. I'll pop this out into its own thing. LDM, I'm not sure that's probably relevant. Models is relevant, I'm sure. Data, I'm going to guess is possibly scripts. Could go either way. And then we just have main.py and some notebook helpers. And an environment and a model card. And the model card, I think, is just basically like a README for Hugging Face or whatever. Maybe we've got like this citation, etc. All right, I think that's basically a README in spirit. We'll start at main.py. Somebody yesterday was asking me to read some Python. And I said I didn't think there were any Python ones coming up, but I guess I had forgotten about Stable Diffusion. Get a drink of water here. Okay. So what are we importing? We're importing Torch, which is the AI framework. I want to say Facebook. Based on Lua. Is that still true? It's used by the Facebook. They have a set of extensions. Maybe it's not a Facebook thing. We have a history. All right. So I guess this does not seem to be Facebook. Um, it's their own group, Torch. All right. At any rate, so we're importing Torch, which is a well-known AI library. We're importing some packaging stuff. That's probably not too important. Whatever Omega conf is, maybe some configuration stuff. And then we have PyTorch Lightning, which I guess was already imported up here. Whatever that is, maybe Lightning is supposed to be for speed and some PyTorch thing. And then we're importing this LDM, which may be this LDM here. But we'll find out. Where did main go? Okay. So we've had this def get parser thing. This is some get parser function, and it's just going to parse command line arguments. That's not especially interesting. We have a wrap data set, which is going to wrap a data set. And why? Or just we have this length function, and we have get item at index. And I guess we just prefer the functional notation instead of the indexing notation. Otherwise, I'm not sure why you would pay the penalty. I guess we like having these underscore things. Yeah, this just seems to be like notational convenience. We have the worker init function. This is going to presumably initialize some worker. I don't know if this function, we don't know yet. I think if this is for training or for inference or both. But we're going to call torch utils data get worker info to get some worker info. And then we're going to get the data set from the worker info and the worker ID from the worker info, really. And that really ultimately comes from Torch. So this is a pretty hard dependency on Torch at this point. And then we check if the data set is an instance of text to image, iterable based data set. So text to image is you write a prompt in text. That's the text part. And just like a Prince album, to means it's going to convert to, and then it's going to convert to what? An image. And then they also support like image to image, where you send it one like starter image and a prompt, and it's going to generate another image from that. We are calculating how, I guess, to split things for parallelism, and we're going to do that by getting the number of records in the data set. And I think this is just integer division in Python. Essentially just division, and we forget about the remainder or fractional part. So we take the number of records, integer, divide it by the number of workers, which should roughly be the number of processors, I would think, on most machines by default. And then we have a comment here. We set num records to the true number to retain reliable length information. Okay. And so we set the sample IDs to what? We look in the dataset valid IDs, and we do some, I guess, computation here. Maybe adjusting for the split size, and so on and so forth. And then we call so numpy to choose randomly an element of what? Something, I guess, in the range between, I guess, by default, it must start at 0. And maybe and a number up to the np random get state at 1. I'm not and this is some, I guess, list because we're taking its length. And what that state is, I'm not sure, but we're choosing some ID from the ID space. So I think somehow this is going to be the right length for the number of the kind of work we're doing. And then we're going to take the state at the current ID, add the worker ID to it, and see the random number generator with that. And I think that all that's doing is ensuring that the um, every worker ID and every current ID gets a different random seed, I assume. All right. That's worker init function. So here's data module from config. We've got some lightning data module. This is the a class from the dependency, and this is our class. So I think this is essentially um, just kind of wrapping the lightning data module um, stuff. We see some configurations for batch size, some dataset configs, the number of workers, etc. Whoops. If train is okay, so we might be doing. I guess train might be a bool, or I don't know what type it is, but it might be none, which might correspond to inference, or rather, this is if not none. Okay, so if train is set, then we set the train's config to whatever train is set to, and we set the train data loader to the self._train data loader. And then we might be, I guess, asked to validate and test and predict and so on. We have this prepare data function that's just going to look in the self dataset config values, iterate over them, and call instantiate from config. And then we have set up train data loader and a bunch of other stuff. This is so far really just like setting stuff up. We have set up callback with some stuff about resume. What kind of type is resume? I have no idea. This is basically just totally untyped Python. We have, this is telling us, I guess, a little bit about what the callbacks are. We have keyboard interrupt so that you can handle the keyboard interrupt. And if the trainer global rank is 0, which must, that might mean we're just starting up, then we're going to, I guess, summon the checkpoint, find a checkpoint on the disk, last checkpoint, and then we're going to call trainer save checkpoint to the checkpoint path. Okay, so no, this is not, well, since we're saving, it seems like we're recording our work rather than loading a previous checkpoint. But I'm not entirely positive. It kind of depends on what these functions do and what last checkpoint means. And I'm not going to dig into that just yet. We also have on pre-train routine start. There's some pre-train routine. It gets started at some point. You pass it in a trainer and a PL module. PL was like was it PyTorch Lightning? And we're going to make some directories like for the log, the checkpoint, and the config. And we handle some callbacks. And whatever omega conf is, we're converting some stuff to YAML, saving some stuff, and so on and so forth. So let's look up omega conf and PyTorch Lightning. Omega conf is a YAML-based hierarchical configuration system with support for merging configurations from multiple sources. Okay. So this is a standard pattern. There's some config files. I guess you can organize the config files in different places and merge them. PyTorch Lightning is the deep learning framework for professional AI researchers and machine learning engineers who need maximal flexibility without sacrificing performance at scale. I don't know why it's called Lightning, but some deep learning framework. Turn ideas to AI. So I'm going to guess that this is I'm going to guess that this is for like doing the, what do they call it? Neural networks and stuff. Okay. Let's see. We have resolver, structured configs. Wait, no, that's omega conf. I want Lightning doc. Basic skills. What if I go here? Train models. But what kind of models? And you can serve models. Okay, well, whatever it is, it's maybe a little bit TensorFlowy in functionality. We have an image logger, which takes a callback, some batch frequency, a max images, whether to clamp, and some like stuff about configuring the log steps. And I guess that the thing that we're doing is we're just writing images to disk. But let's see if that's right. Well, this is the class. This is just the init function on the class. You can log local, which has some, which will, I guess, save in the images directory and so on. So yeah, we're just writing stuff to disk. And we might, I guess we have callbacks like on train batch end. We might do some stuff. If we're not disabled and the module global step is more than 0, and we're supposed to log the first step, then we log the image, which might be locally. And then I suppose there's probably also log remotely. This is log local. It says rank 0 only. I'm not sure what that is. We'll look that up in a second. And if we're not calling log local, then what do we have? We're, I guess, really calling out to the PL module, whatever log images does there. So I'm not sure what that's about. And then we have this CUDA callback. So CUDA is the NVIDIA's framework for writing machine learning stuff onto GPUs. And we have these callbacks like on train epic start, which will take a trainer in the PL module, and it will reset the memory use counter. So you need to record stats for like how much GPU your training is running. They're going to call synchronize on the root GPU, which I have no idea what that does. Is that for multiple GPUs? Possibly. And then we record the start time. And then I guess we're going to clean up. So I wanted to look up 2 things. One was 0 rank 0 only. And the other is CUDA synchronize. Use the rank 0 only decorator imported from the same module, which can be wrapped around any function such that it only gets closed. It only gets called on rank equals 0. Okay, but I'm not sure what a rank is. Now let's look up rank on PyTorch Lightning. Rank 0. I'm just not sure what rank is for this library. Global rank, local rank. The index of the current process across all nodes and devices. What says the AIs? Is there a notion of rank in, let's say, neural networks? There's like matrix rank, but I don't think that that's what they're talking about. But at any rate, it seems to have something to do with. So what is rank in PyTorch Lightning? To the process rank in a distributed training setup. Okay, so this is something about it being a distributed environment. When performing distributed training, multiple processes are launched, and each process is assigned a unique rank. The rank is an integer that uniquely identifies each process. Then there's distributed training setup. Rank 0 is the master process, which will handle tasks like logging, checkpoint saving, and evaluation. In multi-node setups, you may also encounter node rank, which identifies the node, a physical or virtual machine in the cluster. Okay, so it's clear that why 0 is the master rank, but you would think that with rank that there's some comparison operator that gives you semantic meaning, semantic information about the 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 structure. Maybe like higher rank nodes have higher rank processes or something along those lines. I don't know if that's true, but we'll just assume that it doesn't matter. So no, good Nick says so just index or ordinal. Yeah, I don't know. It seems like 0 has meaning, like I said, but I don't know if there's any ordering other than that. Okay, so that's what rank is supposedly. And then the other thing I wanted, so that's why logging only happens on rank 0. If you're logging locally, that makes sense. And then what was the other thing I was looking up? Oh, the CUDA synchronize, which I think I just deleted. I assume that's for distributed stuff as well. Device synchronize. CUDA kernels are asynchronous, so it seems we should call a CUDA device synchronize after each kernel. Doesn't sound right. Blocks until the device has completed all preceding requested tasks. Returns an error if one of the preceding tasks has failed. The CUDA device schedule blocking sync flag was set for this device. The host thread will block until the device has finished its work. Okay, so this really is just synchronizing so we know when it's completed its tasks. Okay. Fine. All right, so that's main.py. That doesn't seem so fascinating. I'm wondering if the magic is in LDM. Pop out LDM here. We have LR schedule, modules, models, and data. And no real README. We have some utility that we're going to ignore. Lambda warm-up cosine scheduler. That looks promising. And then modules, we have diffusion modules, distributions, encoders, image degradation, losses, attention, EMA, and X transformer. Those all look very promising. And what is this? So that's modules. This is modules. And we have autoencoder and diffusion. And then in data, we have init base, imagenet.py, and lsun.py. ImageNet, I'm going to guess, is just downloading ImageNet stuff from the internet. Synset to index has some path. And what is ImageNet? So this is init. Let's see if there's a prepare synset to human. So whatever high box is, we're going to download. We're going to do something with this URL. And this is at Heidelberg University. What if I just take this URL and visit it? And I think I forgot the H. This is some. This looks like a list of labels. So whatever this is, N000004475 is an organism and a being. Or alternately, these may be descriptions of a human. I don't know. These are some sort of labels that are going to be used in the. Oh, are these synonyms? Synset. Noun, a set of one or more synonyms. In metadata, a synonym ring or synset is a group of data elements that are considered semantically equivalent for the purposes of information retrieval. Okay, so those are all, I guess, supposedly synonyms, indexed by whatever those numbers are. And we have this human to integer thing, and we're gonna look on the disk for ImageNet labels and try to open the stuff on this path to read it. And for each, I guess this is a text file because we're gonna read it in split lines, assert that there are 1,000 lines, and build up a dictionary from it. So those are like labels. Oh, here we go. This, I think, is where they download ImageNet. Hopefully only if they don't already have it on disk. And let's see if we can go to this URL. Yeah. So so I think this file really is just about downloading ImageNet and setting up labels and stuff. Let's look up what LDM is. Latent Deer Slate? No. Yeah, maybe. What? Logical disk module. Model? No. Liquid drop model? No. A defensive midfielder. A latent diffusion model, I guess. Yeah, okay. Fine. All right, latent diffusion model. It's the name of, I guess, the fundamental contribution of stable diffusion. All right, so let's look at LDM. This seems to be the place to be. Although I did open all this stuff already. Okay, so there's only the one file in the LDM root folder, which is the scheduler. And I don't know if that's the place we want to start. Maybe we'll start with the models, the autoencoder and the diffusion. And the autoencoder, I guess let's remind ourselves what an autoencoder is. It's a type of artificial neural network used to learn efficient codings of unlabeled data. This is unsupervised learning. It learns two functions, an encoding function that transforms the input data and a decoding function that recreates the input from the encoded representation. So I think that this is a fundamental part of the diffusion model, which makes sense why it's in the LDM/models folder. Let's see if we can find a steps. This actually must be in the paper somewhere, but I don't know if this is the right thing. But basically, I think that what they do is they have, like I believe we'll look this up in the paper, but I believe they did something along the lines of they have a bunch of images. They trained a model on the noisified images. It's relatively easy to add. It's super easy to add noise to an image, and that kind of trains up a model to the inverse of that operation is denoisifying an image. And so I think morally what they do is they start with some prompt and some noise, and they using the model they trained from the labeled data and the noisy images, they they em- they embed the the text prompt in the standard way into some embedding space. And the thing that they do with the images is they somehow use that to nudge the noise in the right direction, and that like kicks off this denoising process, so that the so that you end up with like a denoisified image, and that goes through like the decoder that's the opposite of the encoder that happened on the one side. None of that made sense, but let's let's try to find What if we do something like VAE encoder decoder diagram? I don't know if this is. Let's just go to the paper. All right, here's the paper, and they're comparing to Dolly and whatnot. Let's see if we can find a chart. This looks promising. Where is Zoom? There we go. So the latent space is where like all the magic happens. This is the kind of like machine understandable space. We have some denoising step here. This is pixel space. These are like the description of what the pixels are for each image. If you have something like a bitmap, it just has like byte by byte, like what the colors are there. And so we have some pixely image, and we map it into the latent space, which is the space that uh, the AI algorithm has learned to operate in. And then there's some diffusion process. I'm assuming by diffusion they mean that there's maybe in an analogy with the physical sense of diffusion, and that produces some z sub t. And then I guess we're supposed to follow this flow down here, perhaps, because z sub t goes into this denoising U-net. And these are cross attention layers, I guess. I don't know what these big quadrilaterals are. And then so we use, I guess, attention in the same sense of like transformer attention is all you need, perhaps. Although maybe cross attention is something else. We'll look at that. And then we get here, which is z sub t minus 1. I don't know why we've dropped a layer. And I guess we loop back. Maybe this is saying back into here. I'm not sure. And then we get a Z out, and then I guess we decode into a new image. And what's going on here? I don't know. Some semantic map, text, representations, images. So these are inputs into tau sub theta. And there's a switch here. And I'm not sure what this switch is doing. But let's read more about it. Get rid of this. About that. Okay. So latent diffusion models. Diffusion models are probabilistic models designed to learn a data distribution P of X. That's a probability. That's not a distribution. Just symbol. I mean, the notation. That's I guess X goes to P of X is maybe what they mean. By gradually denoising a normally distributed variable. So we have some Gaussian variable, and we're going to denoise it. I'm not sure what denoising means, which corresponds to learning the reverse process of a fixed Markov chain of length t. So I guess that's probably what the t is here. And the reverse process. So I think that possibly the reverse process here is that they want to reverse the noising process. For image synthesis, the most successful models rely on a reweighted variant of the variational lower bound on P of X, which mirrors denoising score matching. And they can be interpreted as an equally weighted sequence of denoising autoencoders. So these autoencoders are labeled as epsilon sub theta x sub t, comma t, for little t from 1 to the length of the Markov chain. And these little autoencoders are trained to predict a denoised variant of their input, x sub t, where x sub t is a noisy version of the input x. So this is, I think, what I was talking about before. We have x initially, I think, for training, and then we create a noisy variant x sub t, and the autoencoders are trying to predict x, which we know and they don't, I think, for training. And so where do they show up here? Did we see epsilons? I thought we saw epsilon somewhere. Denoising unet epsilon theta. Like, I think that this is like the chain of autoencoders. And I don't know if this kind of looks like they're operating in parallel, but I think maybe it kind of looks like they're operating in sequence, but I'm wondering if I think they probably should operate in parallel, although I don't know. This is in contrast to previous works, blah, blah, blah. Wait, no. Where even was I? Okay, so yeah. And then we have generative modeling of latent representations with our trained perceptual compression models consisting of epsilon and d. So what is this epsilon thing? Big. Is that even an epsilon or is that just a fancy E? I think that's the encoder. Maybe. And D should probably be the decoder. We now have access to an efficient low-dimensional latent space in which high-frequency imperceptible details are abstracted away. Compared to the high-dimensional pixel space, this space is more suitable for likelihood-based generative models, as they now can focus on the important semantic bits of the data and train in a lower dimensionality, computationally much more efficient space. Yep. Okay, so pixels have a lot of information. If you have like 2 pictures of your dog taken back to back, those are a lot of the pixels are different. Maybe almost all of them are different, but there's a sense in which they're almost the same thing. There's 2 pictures of the same subject under the same lighting conditions in the same background, and so there's a lot of stuff that's the same. And so the encoding process is trying to get rid of all the extraneous stuff that doesn't matter so much, and map it into some latent space. And that's what that's about. Then we have this conditioning thing, which I'm not really sure what the switch is about, but basically this is the stuff that how it conditions, I don't know. I guess we'll read about that. Similar to other types of generative models, diffusion models are in principle capable of modeling conditional distributions of the form P of z given y. This can be implemented. Okay, so this is just conditioning in the sense of probability. This can be implemented with a conditional denoising autoencoder, epsilon theta, which depends on z sub t, t, and y. T is the time or like where we are in the Markov chain of length t, of length capital T. Y is the variable we are conditioning on. And z, I think, is what we're trying to estimate. So z sub t is the noisy version of z. And we're trying to find the probability of the real z essentially. This paves the way to controlling the synthesis process through inputs y, such as text, semantic maps, and other image-to-image translation tasks. Okay. All right. So now I have a reasonable mental model of what's going on. But I wanted to look one thing up. And what was that? Over here. Yeah, I want training. And I want to know that, I want to verify that E and D are the encoders. So let's just search for train. Maybe we should have read the abstract. By decomposing the image formation process into a sequential application of denoising autoencoders, diffusion. So this is general for diffusion models. And I think that the thing here is that we're doing latent diffusion. Okay, she state-of-the-art synthesis, blah, blah, blah. Additionally, the formulation allows for a guiding mechanism to control the image generation process without retraining. However, they operate directly in pixel space. Okay. To enable DM training on limited computational resources while retaining their quality and flexibility, we apply them in the latent space of powerful pre-trained autoencoders. And so I guess those are essentially the weights that you download. All right. By introducing cross-attention layers into the model architecture, we turn diffusion models into powerful and flexible generators for general conditioning inputs such as text or bounding boxes, and high-resolution synthesis becomes possible in a convolutional manner. If I skip this sentence here, I don't think it says anything about cross-attention. So we should look up what cross-attention is. Is it related to cross-entropy? And let's bring back up the autoencoder. And I guess let's bring up diffusion model. Cross-attention in transformer architecture. Merge two embedding sequences regardless of modality. For example, image with text in stable diffusion UNet. I still don't really know what UNet is, but I guess that doesn't matter. It's an attention mechanism in transformer architecture that mixes two different embedding sequences. So I guess we have two embedding spaces. They have to have the same dimension. And what do? Just take their cross product? Is that why it's called cross attention? You want, I guess you want another vector of the same length. If you're going to merge them, you can't use a dot product that'll take you back to the scalar space. Except for inputs, cross-attention calculation is the same as self-attention. Okay? Cross-attention combines asymmetrically two separate embedding sequences of the same dimension. In contrast, self-attention input is a single embedding sequence. One of the sequences serves as a query input, while the other serves as a key and value inputs. All right, but what is the actual? So we here's the cross-attention algorithm. Let us have embeddings S1 and S2. Calculate key and value from sequence S1. Calculate queries from sequence S2. Calculate an attention matrix from keys and queries. Apply values to the attention matrix. Output sequence has dimension of length. Sequence S2. So we're taking the softmax of, I'm not sure. I don't remember how we get queries, but there's some, I think, query matrix that we're estimating. So we have the WQ of S2, WK. This should be the key matrix of S1. We take their transpose and we apply them to the values of S1. And then take softmax, which I think softmax is mainly for preventing like runaway numerical stuff. Yeah, it is. Hang on a second. Give me about 1 minute and I'll be right back. Yeah, machine learning is super cool. I'm not up to date. I'm not up to date on the machine learning, as machine learning people can probably tell if they watch this. But ultimately, it's mostly linear algebra from a from a technical perspective, and a lot of that's because that's essentially what GPUs want to process. So softmax takes as input a vector z of k real numbers and normalizes it into a probability distribution consisting of k probabilities proportional to the exponentials of the input numbers. Yeah, we're just going to exponentiate them all and divide by the sum that we get normalized so that their sum is 1. But why are we exponentiating? Is it just to so what will that do? So two zi's that are far apart become super far apart. It derives from amplifying the effects of the exponential on any maxima of the input vector. Okay, so it makes the maxima really stick out, I guess. And I guess it's called softmax as opposed to just taking the maximum. Yeah, that makes sense. All right, I'm on board with that. Here's this thing about cross attention versus self attention. And what is this? These are some attention scores. So these are, I guess, the vectors. You get keys and values from them somehow. And I guess this is trying to tell us that keys are column vectors and values are row vectors. And we get queries from the second thing. And these queries are row vectors. And so we can multiply the queries and the keys if we want to. And these will give us values. And then here's some Python code or something. All right. That's enough for that for now. Let's check out what autoencoders are mathematically. An autoencoder is defined by the following components. 2 sets, the space of decoded messages fancy X, the space of encoded messages fancy Z. Almost always, both X and Z are Euclidean spaces. That is, X is equal to Rm, for some M as in modify, and Z is equal to Rn as in Nancy, for some M and N, two parameterized families of functions. The encoder family, E sub phi, which takes the X space into the Z space, parameterized by phi, and the decoder D sub theta, which takes Z into X, parameterized by theta. What are phi and theta? I don't know, but something. So to train an autoencoder, wait, I guess I should read this. Usually both encoder and decoder are defined as multi-layer perceptrons. That's what I really came for. For example, one layer MLP encoder is the E sub phi of X is equal to sigma of WX plus B, where sigma is an element-wise activation function such as the sigmoid function, or a rectified linear unit. And W is a matrix called weight, and B is a vector called bias. But even though E sub phi depends on phi, it doesn't appear on the right hand side. The right hand side. So I feel like we're just accumulating parameters and they're not really paying off yet. But I think I wrote multiplayer. That could be multiplayer perceptron could be cool. All right, so the multilayer perceptron is the name of a feed-forward artificial neural network consisting of fully connected neurons with a nonlinear activation function, organized in at least 3 layers, notable for being able to distinguish data that is not linearly separable. Okay, oops, I didn't mean to click on that. So they're fully connected neurons, so I guess that means everything is connected, and then we have some nonlinear activation function. I think some version of tan is what I saw. So the two historically common activation functions are both sigmoids. They are described by y of v sub I is the hyperbolic tangent of v sub I. And then here's another one. We're just going to take 1 plus e to the negative v sub I and take that's multiplicative inverse. Okay. So that gives us a little bit of a sense. And I just want to verify now that E in these diagrams are encoder, is some encoding, and D is some decoding. More precisely, given an image X in R of height, I guess this is probably height by width by 3. 3 is probably the RGB values. In RGB space, the encoder, fancy E, encodes X into a latent representation. Okay. What was the point of all that? I wanted to verify what we were doing with the autoencoder.py files, and that there's the right way to think about this is encoding, doing some monkeying around, and decoding. And then what we learned along the way is that the monkeying around largely consists of autoencoders that are more or less learning, I think, specific features. So if you look at the neocortex, this may be a bad image search. There's famous studies where we figure out that that there are different like cell clusters that correspond to detecting certain parts of images, like edge detection or like maybe circle detection, that sort of thing. And then I also wanted to know whether these are running in parallel, but I kind of get the impression that they're serial. At any point, let's move back back to the code after that long diversion. So here's autoencoder.py. We have a VQ model, M-O-D-E-L, which is an extension of the Lightning module. And it takes a bunch of config like dd config. I don't know what dd config would be. Loss config is some, presumably some description of the loss function. I don't know. I think loss function is just the same as a negative reward function, right? Yeah. Okay. So this is just the I guess we're trying to minimize the loss function as opposed to maximize some reward. We have some stuff like coloring, labels, some thing like we could ignore some stuff, we can set a path, etc., etc. And we set self.encoder to capital E encoder of, I guess, instantiated from the dd config, and similarly with decoder. Can we find encoder and decoder? Maybe not. So those are in X transformer. And so since those are probably relevant to understanding, let's take a look at them. So encoder extends into attention layers, and we're just calling super init, saying that they're not causal. And what is decoder? Is this right? Decoder's in a separate file? A different file than encoder? Oh, okay. I guess we have different encoders. So here's one encoder in ldm/modules/diffusion modules/model.py. And encoder is going to be an extension of nn.module, which is torch.nn, presumably torch.neural network. Okay. So this is a neural network, I think is what it's telling us. And we have a ch and an out ch. I'm guessing these are channels. We have ch mults, the number of resolution blocks, result blocks, I don't know. Attention resolutions, I guess now is resolutions. Dropout. So dropout is set to 0. Dropout is used, if I'm understanding correctly, in the what's it called? in the like transformer world and possibly elsewhere, dropout is a way of, as you're training the neural network, you simulate having a lower dimensional space by randomly choosing some neurons to kill off temporarily during that training step or during a few training steps or whatever. And that reduces overtraining, and is kind of similar, I think, in spirit to training something like a random forest, having training multiple similar models and kind of averaging over them is a general trend. And dropout is used as a way to, because you're dropping out random neurons each time, you're approximating the training of a bunch of different neural networks. So it seems like a cool idea to me. I'm not sure why it's set to 0 by default. Maybe they experiment with different settings of it. Resample with convolution, convergence, probably some version of convolution. I think, I don't know. Input channels, resolution, Z channels. I don't know what Z channels are. Double Z, use linear attention is false, and attention type is vanilla. And these are probably all configurations from the torch.nn thing. And this is just setting some stuff up. We have this downsampling, self.conv in. We're going to call torch.nn conv2d on the channels. And now we can look up conv2d. And as we would expect, it applies a 2D convolution. Applies it, as we would expect, it applies a 2D convolution over an input signal composed of several input planes. So this is some 2D convolution. We set the current resolution. Whatever this channel multiplicity thing, I guess that torch and then has some notion of channels. In channels. So there's some notion of in channels, I guess. I don't know if these are like sending messages to each other or what. We have self.down, which is a module list. And I think we're still doing something called downsampling. And for eye level, in range self.num resolutions, did this have a default? Yeah. The number of resolutions is the length of the ch-multi, the ch-mult. All right, whatever these are, we are going to loop over them. Number of resolution blocks, I guess. And then we are going to call block is some module list, some like torch neural network module list, which probably means it has, it's probably a list that can be like maybe shared between different processes or threads and is like GPU appropriate or whatever. But I'm going to think of it basically as just a list. And we're going to append to that list a ResNet block, passing in some in channels and whatnot, and the dropout. And then we're going to set block in to block out. And these are two different something or others. And if the current res is in the attention resolutions, then we're going to append to attention something that says that we're going to make an attention, I guess like an attention, probably make an attention layer, passing the block in and giving it the attention type. So I think that probably make attention is from torch, although it's not modified here. Do we have like def make attention? The make attention does seem to be defined by the stable diffusion repo. But let's see if we can figure out what it is. So we're doing some asserting. We check if Xformers is available. And if they are, and we're using vanilla, then we set the attention type to vanilla Xformers. And if the attention type is vanilla, then we're going to assert that there's no keyword arguments. I guess you only need keyword arguments if you're configuring some less vanilla type of attention. And then we return an attention block. We might return a memory efficient attention block or a memory efficient cross attention wrapper, or the identity matrix if we have no attention. Let's see what attention block is. So you'll notice, I think on this channel, I don't usually do a lot of chasing things around. Sometimes I do. It kind of depends on the code style. And in this case, I'm chasing stuff around because you kind of need to know what all the building blocks are, and we're using a lot of libraries and stuff. All right, attention block is here. Do we think that they defined it? Yeah. So an attention block extends nn.module. We have some channels. The self.norm is going to be, we're going to normalize the in channels, whatever normalize is. We're going to, I'm going to guess Q is queries, K is keys, and V is values. And we're going to call this 2D convolution, passing the in channels, setting the kernel size to 1, the stride to 1, and the padding to 0. And the same is true of self.k. In fact, is there any difference between these? In channels, kernel size 1, stride 1, padding 0. So I guess these are just creating like matrices of the appropriate size. I don't know. I don't know how these are differing. Maybe these are just initializing them and they differ eventually through training. And then we have self proj out. And that's being passed the same stuff. That's the initialization. Let's see what else happens. On the forward step, we pass in X. And we set H underscore to X. And then normalize it. And then we set Q to self Q of H, etc., etc. The same with Q and V. And then we compute the attention. We get this. We ask for the shape of Q, which gives us B, C, H, and W. I guess this is like the submatrices or something that make up Q. And then we reshape it. We reshape Q according to what? We pass in B and C. And now we multiply H and W. H and W is possibly height and width. And then we permute Q. Possibly this just switches to whatever 2 and 1 is. It seems to be switching these two arguments. Then we call reshape on K, passing in H times W. Again. So the shape should be, I see. The shape isn't giving us anything that's making up Q. These are just the dimensions, I guess, of Q. And I think H is probably height and W is width. I'm not sure what B and C are supposed to be. But similarly, we reshape K. And then we call torch BMM on Q, comma K. So this should be we get W back. So this is the queries, I believe, and this is the keys. So we're going to look up the keys and we get W. And what is torch BMM? I don't know. Batch matrix product. of matrices stored in input and mat2. Input and mat2 must be 3D tensors, each containing the same number of matrices. Okay. So if input is a b by n by m tensor, mat2 is a b by m by p tensor, the output would be a b by n by p tensor. What is b? I'm not sure. N by m. I guess b is batch size. I'm going to think b is batch size. That makes this an n by m matrix, which sounds good to me. This is m by p, which you would get by trying to avoid using O as a variable name. You don't want to use O as a variable name because it looks like 0. So I think that what this is saying, this is an n by m matrix. This is a matrix that has the same number of rows as this has columns. And we're going to, they have the same B because they have the same batch size, is how I'm going, how I'm going to assume that this is going on. The thing that we get back is B, which batch size, and it's n by p, which is the shape you would expect if you multiplied an n by m matrix with an m by p matrix. So that's what I will assume is going on. And so now that we know that this is batch, I still have no idea what C is. Maybe it's just some part of the some dimension. Colors, color, height, and width. Let's assume that's true. So then this is batch size, color, height, and width. And then we're gonna maybe permuting them because we want color to be the last one instead of height times width. Okay. And then what W is, I have no idea. But that's the result of multiplying the queries by the keys, which is the way that key lookup works in transformers. And we set W underscore again to the thing that we got from the batch multiply. And we're multiplying it by converting C, I guess, which is the color vector under our theory, taking its 1 over the square root of it. And I'm assuming that when you multiply a tensor with the star operator, that this is going to multiply every row of the matrix or tensor. So I guess this is somehow normalizing the color space. The colors don't get too crazy or something along those lines. And then we're going to take the softmax with dimension 2. And I don't know how that works with respect to the fact that I believe we're in a batch. So I don't know if this is a batch-wise softmax or if we're taking the softmax over everything that's everything in the batch, if that makes sense. Like, I don't know if let's assume this was a real max. I don't know if this is like one max per batch element or if this is like the max among all of the batch element maxes. All right, at any rate, now we attend to values. We do some more reshaping and permuting. We do the batch multiply to get h's. So W must now be width, I guess. Then we get this h that we just reshape it and we project it out. And we're going to return x plus h underscore. So that's the forward step. I don't think we've overwritten q, k, or v. So they, at this point, are still the same as whatever this conv2d thing was doing. And that's it. I feel like this can't be right. There must be some some way that QV and whatnot get updated. But where would that be? Let's look at the conv. No, let's just ask the AIs. what it thinks about this. We'll say, tell me about this code. So it says in channels is the number of input channels, as opposed to, I guess as opposed to the channels themselves, it's just the number of them. Stores the input channels for later use. Norm initializes a normalization layer. Okay, so so this is initializing a normalization layer, and so I guess we're building up like a graph of computation that we're going to pass into the GPU eventually, as opposed to actually computing something. At least that's how I'm reading ChatGPT. ChatGPT could be wrong, and I also could be wrong. So there's a lot of noise there. And then Q, K, and V are convolutional layers with a kernel size of 1 by 1, no stride, and no padding. And then proj out is for, it believes, projecting the output of the attention mechanism back into the original space, which makes sense. And then the convolutional layers creates a 2D convolutional layer. The parameters passed include what? Yeah. So I guess am I correct in thinking that this is just setting up layers, and that at this point Q, K, and V are identical? Okay, so somehow they get modified. I think they get modified in training. Oh wait, did I tell it about forward? Or is it just quoting from memory? When you implement the forward method, you pass the input through these layers. Yeah. So the Q normalized Q applies the Q convolutional layer to the normalized input, producing the query representations, etc. I guess maybe they don't get trained; they just get modified by the thing that we pass in, by X. Is that right? And we return X plus H. Okay. Yeah, I guess that's right. So we're not. So does that mean the Q, K, and V don't get trained over time? Instead, they recompute their values for each X passed into forward. It's essentially like a stateless. No? So for each input, the X is passed to the forward method. These computations use the current weights of. Okay, so let me ask about this then, because I guess that it's saying that occurs like as a what's it called? That's not explicitly happening. We're not like resetting k self.k, self.v, etc. But I guess that when we evaluate, is that when it's doing the training? Let's ask. Let's find out. So here's the forward step. Which lines of code modifies the trained values of, say, self.k? The code in the forward method does not directly modify the train values of self.k during the forward pass. The forward pass computes the output of the network. However, during the backward pass, the gradients of the loss with respect to the weights are computed. Oh, okay. Is that what it means by backwards? Okay, so we'll look at the backward. Hardest attention and transformer are the most complex mechanisms. So there actually, maybe at some point we'll look at the attention and transformer paper. I think that they're actually pretty straightforward. I don't remember I don't remember them off the top of my head. But I feel like mathematically they make sense. Maybe what they do intuitively is less clear. But also I think that there's an element of you try different things mathematically, and the ones that work are the ones you keep. And whether it makes sense or not is kind of more like something you get used to. I think there's an element of truth to that. So here's self.model. Let's see if we can find the backward. Or maybe the backward pass is not implemented here and is just part of the library. We have this back here. And we have some references to backward compatibility. We have this checkpoint function and this static backward method, which has a context and output grads, which I think, if I remember Python correctly, this the star operator takes a tuple and passes the values of the tuple in as ordinary arguments to the backward function or something along those lines. And at any rate, we take the context and assign input tensors based on whatever x is. I don't know where x comes from. We're going to detach. Oh, no. So we're going to iterate over the input tensors from the context. So that they all require the gradient and reset the input tensors to that. And then we're going to, with torch.enable gradient, we are going to call cuda.amp.autocast. I don't know what autocast is doing, but some sort of maybe changing types, casting types, I don't know. And creating some shallow copies and calling context run function on the shallow copies. And then we're going to set the input gradients to the output of torch autograd.grad on the output tensors. The passing in the input tensors plus the input params. I think this is just list concatenation. And the output grads. And we are allowing unused. Then we're deleting a bunch of stuff. And we're returning none plus input grads. Okay, so this is doing some gradient computation using CUDA. And the thing we're getting back is essentially just the input gradients. I'm not sure what they're considering output gradients versus input gradients. And I don't know what they do with the input gradients. That's computing them, but where do we use them? Yeah, I don't know. At any rate, let's go back to somewhere else here. This is the encoder. This is the forward step. This, I think, was something about downsampling, doing something with blocks. I'm not really sure what the blocks are, but we're building them up depending on the number of resolutions. We have some middle thing, middle blocks, H, tem B. I don't know what tem B is. Temperature? I don't know. But something. Um, and there's this is like a ResNet block. Let's look up what ResNet is. Residual neural network. A seminal deep learning model in which the weight layers learn residual functions with reference to the layer inputs. It was developed in 2015 for image recognition and won that year's ImageNet Large Scale Visual Recognition Challenge. We have a diagram here. We have X. This is, I guess, the identity function. And it goes through some layers. And we return X plus f of X. A residual block in a deep residual network. Here, the residual connection skips 2 layers. Okay. Hi. I hate YouTube Live. Sorry. It may be my I'm on minimal delay. I tried like ultra low latency, but YouTube complained that it wasn't able to there'd be too much buffering. At any rate, we have this ResNet block, which is some implementation of ResNet stuff. I don't really understand what's going on with ResNet yet. And we have, and this is the basic attention block that we looked at. Here's a linear attention block. And we have this make attention that's going to really just dispatching based on your parameters, what kind of attention block to use. And then we have a model. I don't think we've looked at this yet, but it's another torch NN thing. We're passing in a bunch of channel stuff, some attention resolutions, dropout, etc. We might be using timestamps. I think we did look at this. So this is the downsampling. This is iterating over blocks. We have another module for down. And I'm not really sure what downsampling is. We have the middle thing here. We have a middle ResNet blocks. So I think that here we're still building up a network. We're building up the, I don't know what you call it, but it's like a collection of neural networks and attention layers. And just building up kind of like a graph of all the machine learning Lego blocks that we're going to use, I think is what's going on. So for example, we have some attention layer, which is mid attention 1. And then we have mid block 2, which is some ResNet block. So this is some, it's like a layer cake or a lasagna with attention layers layered with like ResNet blocks, it looks like. Downsampling, what it's calling downsampling might be the same as like encoding. So it might be the part, they might be calling it downsampling because we're reducing the, we're mapping into the latent space, which is reducing the dimensionality. Because at the end we do upsampling again. Where did it go? I think here, upsampling for eye level and reversed range, blah, blah, blah. We're going to call self.up. You know what? I think that what they're doing maybe is, scratch what I just said, whatever torch cat is. I think that what they're doing is they're taking an image, subdividing it into some number of blocks, and then replacing the image with what you get by doing some sort of averaging operation on each of those blocks, which is just going to reduce the size of the image, which is possibly similar to what they do when you like downscale an image in a photo editor. I think maybe that's what it's doing. And so this is kind of like a compression operation, I think. And then we are operating on the compressed image potentially, and then trying to decompress it. And I'm not sure what self.up and self.down do. See if we can find def down. Let's see if we can find, I keep hitting the key to move this, and it keeps bringing up this menu. Try to stop that. Let's try torch NN down, up. Interpolate. Down, up samples the input. The tensor interpolated to either the given size or the given scale factor. Okay. Currently, temporal, spatial, and volumetric sampling are supported. Okay, so maybe the way I described it is not the way to think about it. It may not even be true or close to true. I guess this is maybe the way to think about this is we're sampling parts of the image and training based on the samples. They call it a computation. Thank you. No good, Nix. It's hard for people to be. Is it hard for people? With only a software development background, probably. I mean, you need to know math that is not typically, I think, taught as part of software development. But I bet that the libraries are so good that you should just try it. I think you should just try, if you're interested in it, try training some stuff, because like there's only a handful of people. Let's take a place like Google or Facebook, or I guess Meta is what it's called. I think that there's really only a handful of people there that are like pushing the envelope on new mathematical AI stuff. And then everyone else there is basically a user of what those people do. So there are a handful of like major papers, like the Transformers paper or the attention paper or the bird paper, and everything else is it's just kind of like using that stuff, training on more data, making smaller optimizations here or there. So I think everything is the same way that you don't really need to know these days about what exactly is going on physically with the CPU or power management to get coding done. I think you can probably abstract away from a lot of the AI specific stuff and just treat it as like a coding project where you black box as much as you can. So that's how I would approach it and see if it works. May work, it may not. All right, so here's the autoencoder file. We have a VQ model. I don't know what VQ is. Probably value query, maybe. And we have this encoder and decoder. We're going to instantiate some vector quantizer. Vector quantizer, I guess, is what VQ is. So we have some vector quantizer, which has some stuff with embeddings. So we have an embedding dimension, whatever beta is, and I don't know what remap and something about shape, keeping this shape sane, and then whatever n embedded is. N embed is passed in, right? So I guess that possibly what we're doing is we have some vector, which is maybe what's in n embed, and we're going to embed it and possibly also quantize it. But we'll see what happens. So we get this self.quantize thing. And then we have this quant conv. We're going to call torch nn conv2d. Something about z channels with the embedded dimension and whatever one is doing. And then we have post quant conv. And somehow we've switched these two arguments. So dd-config z channels is now the second argument as opposed to the first. And embed dim is the first instead of the second. But one remains the same. I don't know why we are doing that. We might colorize the labels, which I'll ignore. We might monitor, which I'll ignore. And then we have this batch resize thing. We might use EMA. I forget what EMA is, but this is setting it up. We have some checkpoint path. And we may initialize from checkpoint. Then we have a scheduler config. And we have this LRG factor, which we'll see in a moment, I think. EMA exponential moving average. Maybe? It can't be right, is it? Well, I don't know. Lit EMA. Let's look at lit EMA. No. Okay. But let's also look up, what is it? Vector quantizer. Vector quantization. A technique from signal processing that allows the modeling of probability density functions by the by the distribution of prototype vectors. Okay, so we have some prototype vectors, and somehow we're going to feed these into a model, and it's going to model a probability distribution. It's originally used for data compression. It works by dividing a large set of points, vectors, into groups having approximately the same number of points closest to them. Okay. So it's kind of like k-means, right? Okay, here we go. So represented by its central point, as in k-means, and some other clustering algorithms. Okay, so it's kind of like I'm going to think of it as a clustering algorithm. All right, so this is some way to cluster things. Maybe we're clustering by embed dimension. Let's see if we can find out the API for vector quantizer. Is this a PyTorch thing? Taming.modules. So this is from the Taming Transformers repository in CompViz. And so this is the same group of people, but a different repo. Discretization bottleneck, part of the VQVAE. The NE is the number of embeddings. EDIM is the dimension of the embeddings, and beta is the commitment cost used in loss term. And so this is just some, I guess we're taking the difference between ZE of X and SG of E, whatever that means, squaring it to get some distance, and then beta is like a weight on that term somehow. This class contains a bug regarding beta. Okay, this somehow buggy. VAA is what? Variational autoencoder? Variational autoencoder. The basic scheme for a variational autoencoder. The model receives X as input. The encoder compresses it into the latent space. The decoder, the decoder receives as input the information sampled from the latent space. So we encode it, we sample it, and produces X prime as similar as possible to X. And what is the point? I think the point is to try to train the encoder and decoder. In addition to being seen as an autoencoder neural network architecture, variational autoencoders can also be studied within the mathematical formulation of the variational Bayesian methods. Yeah, connecting a neural encoder network to its decoder through a probabilistic latent space that corresponds to the parameters of a variational distribution. Thus, the encoder maps each point, such as an image, from a large complex dataset into a distribution within the latent space rather than to a single point in that space. I mean, that's a good point. It's a distribution. It's like a smear over points in the latent space rather than being a single point. You can imagine trying to make a latent space where like the concept of dog is a single point or whatever. The decoder has the opposite function, which is to map from the latent space to the input space, again according to a distribution, although in practice noise is rarely added during the decoding stage. By mapping a point to a distribution instead of a single point, the network can avoid overfitting the training data. Both networks are typically trained together with the usage of the reparameterization trick, although the variance of the noise model can be learned separately. With a prior and noise distribution, blah, blah, blah. Yeah, I think what this is saying is that I don't know if we add noise during this step, but we're trading the encoder and decoder simultaneously. And the idea is to factor it through this space and get something out that's good. And this then provides really just a kind of compression that you can lossy, but that allows you to do sampling and machine learning tricks in that space. So I guess that's what we're doing with this VAE file. I think, was it in a separate window here? Where did you go? Variational autoencoder. Get rid of this. I don't know where it went. Let's just pull it back up. Oh, it's just called autoencoder. All right, whatever. Okay, so this is the VQ model. Is there another version? Is it just this one implementation? We have a VQ model interface, an autoencoder KL. I'm guessing like KL divergence. Identity first stage. I don't know what that's about. Let's look at autoencoder KL and just see if this is something about the KL divergence. We've got some encode step. We call self.encoder on X. What is self.encoder? It's just this encoder thing we defined. We tried it, I guess we compute its moments using quantconv. Where is quantconv? It's this three-dimensional convolution. And then we get a posterior, which is, I guess now we're, the Wikipedia just told us that it's related to some Bayesian, I guess, interpretation of autoencoders. And so this naming this posterior seems to highlight that. And we call the diagonal Gaussian distribution passing in the moments that we somehow estimated from here. And this gives us a posterior distribution. And then decoder, we're going to call post quantconv. I guess post meaning afterwards, since this is the encoder and this is the decoder, which happens post sampling, I guess. And then given the quantconv, we just call self.decoder on Z. That gives us dec, the decoding. And in the forward step, we set the posterior to be, we're going to encode the input. And if we have sample posterior set to true, which it is by default, we're going to call posterior.sample. I guess somehow we configure the amount of sampling that we're doing. Otherwise, we're not going to sample, we're just going to get the mode, I guess, of the posterior distribution. And then we're going to set the dec thing, the decoded thing, to be the thing that we get by calling the decoder on the sample we got from the distribution. And then we're going to return both the decoded value and the posterior. I don't know what get input is, but we're doing some sort of permutation. And then the training step is we're going to get the input from the batch and the image key. And that gives us inputs. And then we're going to initialize the same class, the autoencoder KL, as ourselves. And that's going to give us reconstructions and the posterior. I'm guessing reconstructions is maybe the same as what they call dec here. And then if the optimizer index is 0, then what? We're going to call the loss function on the inputs, reconstructions, posterior, etc. The last layer is whatever self.get last layer points to. And the split is equal to train. I'm not sure what that means. I guess there's some training split. We're going to log some stuff, and then we're going to return the loss that we computed here. But if optimizer index is equal to 1, then again we compute the loss, but we call it disk loss. And are there any differences? Not really, although we do pass in the optimizer index, and we return the disk loss. And really the main thing is we're calling it something different, maybe. And then we have a validation step where we get the inputs. We get the reconstructions in the posterior. We compute the loss and the disk loss. How are these different? We're passing in 0 versus 1 here. And that's really just optimizer index, right? Logging some stuff and then returning the log dict, the dictionary of loggable stuff. Does that count as validating? I don't know. I guess we're just recording stuff. And then we can configure optimizers. Like there seems to be this atom optimizer. Implements the atom algorithm. Adaptive moment estimation is an iterative optimization algorithm used to maximize the loss function during the training of neural networks. And it's a combination of RMS prop, maybe root mean square, and stochastic gradient descent with momentum. I don't know what RMS prop is, but I'll read about it later. Okay. Cool. All right. So we're starting to see things that look like stuff that make more sense to me. So we're seeing probability distributions. We're sampling from them. Here's 2 RGB. This is just catching my eye. We have some image key, which is equal to segmentation. I guess this is only run if we're trying to segment something. And we call conv2d with weight equal to self-colorize, whatever that is. And we have this max min thing. I guess this is like normalizing the colors or whatever. Right, that's not so interesting. Okay, so I still haven't seen anything that... I don't know how to spell, is it Kublak or Liebler? Pullback? Yeah, I don't know what the KL is for. We have these other, we have the vector quantization model. That's going to be more autoencoder stuff. And does it have its own training step? Or this looks the same as it did before? Okay, so that's autoencoder. I guess we'll leave that there. What else is of interest before we go? So we have a classifier, DDIM, DDPM, and PLMS. I think these are the samplers, right? Now let's look at classifier. Encoder UNet model. I still don't know what UNet is. It's a convolutional neural network that was developed by a biomedical image segmentation. It's a U-shaped model. Comprises convolutional layers in 2 networks. First is the encoder, which is followed by the decoder. I guess this is why it's called UNet. It's a big U. This probably would have explained some of the code. We have some big image, 3 by 250. That's not that big. So 256 by 256 with 3-dimensional color. We'll down conv 1. I guess this is probably the downsampling. Max pool. Down conv 2 again. Max pool. Down conv 3. Max pool. Down conv 4. I guess we'll concatenate. So we'll upsample 4 maybe and concatenate it with down conv 3. Up conv 1. And concatenate after upsampling with down conv 2. Then up conv 2. Upsample. And what? Concatenate that with down conv 1. So we're kind of we have these like downward convolutions, and we're kind of concatenating the. I'm assuming downward convolution is a kind of degradation or compression step, but it seems like we're at each step concatenating it with something that's higher resolution or something along those lines. And this gives us k by so 256 by 256 masks with whatever k is. K used to be the number of colors, but maybe now k is less than 3. Maybe if it's like black and white or whatever. Something like that. At any rate, so here's classifier. What are we classifying? We have noisy latent image classifier. And I guess this is just classifying images. This is the number of classes. Some stuff about checkpoints. Load classifier. This is, I don't know, writing logs, training step. So I think that this is just an image classifier, basically the kind of the opposite of what we trained for from the ImageNet stuff. What is clip? Contrasting language image pre-training. All right, this doesn't seem to be related to that. But let's look at DDIM. This is a sampler. It just extends object. I would have thought it extended some sort of sampler. But we've got this register buffer thing, which some torch CUDA stuff, and we have make schedule, which takes some DDIM number of steps, what kind of discretization the ETA, and whether it's verbose. And I guess this is the fact that make schedule depends on DDIM specific stuff is probably why there's not a more general like sampler class, because the arguments would all differ depending on the kind of sampler. But we call it make DDIM steps with setting the discretization method to DDIM discretize, etc. Whatever alpha's cumulative product, I assume is what this is. And we're going to do some assertion on the shape. We have this lambda in the middle of a sampler. We're just calling clone. I'm not positive that's high performance, but what do I know? Then we're registering a bunch of buffers, betas, alphas, cumulative product, etc. Registering more buffers, and so on and so forth. And then sampling. So maybe this is not in the middle of sampling, this lambda. Maybe this is just, I don't know how often this is called. But the actual sampling is going to do the sampling somehow. We do call make schedule within every sample. And we call self DDIM sampling, which I'm not going to look into. I'm going to just cut it. I think DDPM is similar. PLMS is going to be the PLMS sampler, which may be interesting to look at, but may not be. As I mentioned at the start of this code is at least 2 or 3 years old, which I think probably makes it mostly ancient from a machine learning perspective. I don't know if you were to rewrite this again today, you would use exactly the same libraries. Maybe you would, maybe you wouldn't. I just don't know the field. I'm going to go soon, but before I go, let me just double check to see if there's anything I really wanted to see. I think I wanted to see LR schedule. Let's see what's in distributions. I'm guessing those are probability distributions. I think we exhausted model, or maybe not. We have the OpenAI model and model.py. And we looked at encoders. These are different loss functions, I guess, and I'm sure that these are like well known in the literature, but those are going to be implementations, I guess, of different loss strategies from the literature is my guess. And then what was in models? Diffusion and autoencoder. So this DPM solver, I don't know how that's different from. So this has both a solver and a sampler. Maybe DPM is solving some PDE or something. Here's LR scheduler. what is LR? I don't know. Left, right? Nope. Lambda warm-up cosine scheduler. LR warm-up. We have some min, max decay steps. In schedule, if n is less than the warm-up steps, then we set LR to be this computation. We're going to divide some stuff, and that has to do with the start and the max, distance from how far are we from the max, and we're going to divide by the number of warm-up steps times n, and we're going to add the start. And we'll set the last LR to the thing we just computed and return LR. Otherwise, we've already warmed up. We'll set T to whatever this thing is. Some computation with the warm-up steps and the decay steps. T will be the minimum of T and 1, so that we, I guess, never go below 1. And we'll set LR to the min LR plus half of taking the difference between the min and the max and multiplying that by 1 plus cosine of pi times t. This is oscillating, but this is kind of clamping it to being above 1. We never like oscillate below 1 or whatever. And we set last LR to the thing we computed, and we're returning LR. And why? Let's look up cosine scheduler. Learning rate. Ah, I see. Yeah, that's probably almost certainly correct. Okay, and so based on this, I'm going to guess that the reason the learning rate has this oscillation behavior is for annealing. So I think the trade-off is if you learn too quickly, the downside is probably what, like overfitting. If you learn too slowly, the downside is you spend a lot of resources on learning things, and you may not converge to anything actually useful. Hello, Mr. AM Blogger. I think you were the one asking me yesterday about Python, and I had totally forgotten that there was that stable diffusion was a Python repo. So we're actually looking at Python today. Although we're almost done. Okay, so that's my guess. And so there are these there's like simulated annealing, which classically you kind of heat up and cool down. Sometimes you take bigger steps, sometimes you take smaller steps, and I'm going to guess that this is kind of tying the size of the step to the cosine function. But we'll see. Let's see if that's true. Set the learning rate of each parameter group using a cosine annealing schedule, where eta max is set to the initial learning rate, and t cur is the number of epochs since the last restart in SGDR, whatever SGDR is. When last epoch is -1, sets initial learning rate as LR. Notice that because the schedule is defined recursively, the learning rate can be simultaneously modified outside the scheduler by other operators. All right. Deprecated. Verbose is deprecated. Okay. Now let's see if there's a thing on cosine annealing. Let's ask Gemini. Cosine annealing is a technique used in machine learning to adjust the learning rate during the training of a neural network. It controls how much of the neural network updates its weights based on the errors it sees. A good learning rate can help the network converge on a good solution faster, while a bad learning rate can make training slow or even prevent the network from learning altogether. So cosine annealing is a specific schedule for adjusting the learning rate over time. It follows a cosine curve, starting at a high value and gradually decreasing to a low value over a set number of epochs. Okay, are we just decreasing? Why not just use monotonic function. Large initial rate, gradual decrease. That include you may also include restarts where the learning rate is periodically reset to its high starting value. Okay, so why use a periodic function for gradual decrease? Why not a gradually decreasing monotonic function? Thank you. Thank you, Mr. AM Blogger. Why? That's a good question. It is a good question. Somebody, who was it? Some uh, well-known ex-Googler was tweeting the other day about how Gemini is always kissing your butt and complimenting you on your questions. Here's why cosine annealing, a periodic function, might be referred over a simple gradually decreasing monotonic function. Exploration versus fine-tuning. It allows for a period of exploration early in training at a higher learning rate. It's also true of a monotonic function. It wouldn't. Oh, okay. Wait, what? Why not? Warm restarts. Does the cosine, what is it called? In cosine annealing, does the learning rate ever increase, or does it always decrease over time? The learning rate does not increase. So it sounds like if Gemini is right, then I was wrong. Okay. Let's verify this with ChatGPT. Not that this is any actual sort of verification, but we can at least slightly guard against the possibility of hallucination. You start with some initial learning rate, eta max, and a minimum learning rate, eta min. So you're going to take the min plus half the distance between the max, which is what we saw, plus 1 times 1. So these are constants. And then we're adding 1 plus t pi over big T. I think T is a constant. So this should oscillate. Smooth transition. Higher indicate the improved generalization. Creating deep neural networks. Does the learning rate monotonically decrease? It does not monotonically decrease. Instead, it follows a cosine curve, which means it oscillates, decreasing and increasing within a cycle. Yeah, that's what I thought. I thought it was going crazy, Gemini. So let's try. I don't have a good package here for graphing here, so we'll just take this. We'll just use Mathematica. So what is eta? Eta is the minimum learning rate. I have no idea what a reasonable learning rate is. But let's say the minimum learning rate is 0 and the maximum is 1,000. And then what? 1 plus. And then T is the training steps. Let's say that there are 50,000 training steps. And we will just say, you get this right? There's a pi here. I don't know why I was expecting this to be damped, but it's not actually damped. We're just always above 1. Okay. So it really is just oscillating. Let's try reducing the size here. Okay. So that's cosine annealing. It's uh, maybe the way to think about it is it's balancing exploration and explore and exploit. Where's the equation again? In my mind, I had decided that this was damped and that over time you would oscillate less frequently. But I don't think that's the case. Well, there's this warm up bit, and then yeah, we're just taking one, and this is just basically a cosine. And then everything else is a constant. I think we're not like dividing by um, we're not dividing by like t or any function of t. Okay, so that's the learning rate schedule. That was interesting. I hadn't really heard of cosine annealing before. Distributions, we have the Dirac distribution, which should just be infinite probability on one point. We have the diagonal Gaussian distribution, which is maybe a multidimensional Gaussian where I don't know. Diagonal Gaussian. A distribution with a mean and sigma vectors, which you could fully describe a distribution with a diagonal covariance. Each entry of the random vector would be uncorrelated from one another. Yeah, I don't know. I'm guessing this is like a. I'm guessing that what they said is correct. That the covariance matrix is diagonal in this distribution. Whatever KL here is, self other is none. If other is none, then we return half of the torch sum of some stuff. Otherwise, we include other in there. I think this probably is maybe the KL divergence, but I don't know. Yeah, compute the KL divergence between two Gaussians. Okay, so this is the whatever the diagonal Gaussian is, some diagonalized version of maybe multidimensional Gaussian, or maybe just two Gaussians that have come to meet each other. And then we have open AI model, which we have this thing adapted from clip, attention pool 2D. I don't know what that is, but I have to go in a couple of minutes. We have this thing, upsampling, an upsampling layer with an optional convolution, and so on, downsample. And in diffusion models, we have get timestamp embedding, et cetera, upsample, downsample. There's probably some cool stuff here. Maybe hold on just 1 second. while watching your stream and installed a portable air conditioner. I'm so glad. That's great. Okay, so I'm back in diffusion model. Sorry, diffusion modules slash model.py. And we have this upsample and downsample stuff. And forward for upsample, the forward method, which I have no idea. I guess that like when you use the this neural network.com 2D thing, you're supposed to implement the forward method, maybe for all torch and NN stuff. I don't know. Or maybe, I guess, maybe for all NN modules. But we're calling interpolate, which we saw before, with a scale factor of 2, using, I guess, nearest neighbor is probably what nearest refers to. So this is taking something lower resolution, making it higher resolution, I guess scaling it to twice as large. Downsample should be the inverse. We're going to pad. I'm not sure why, but we will. And otherwise, we might try to call average pool 2D with a kernel size of 2 and a stride of 2. And I don't know what those 2s are doing, but maybe those 2s are the inverse of the 2 here. Maybe somehow this is scaling it down by a factor of 2. And then I think we saw some of this stuff like ResNet block and attention block. I'm not really sure what this OpenAI model was doing. Where did it go? So the OpenAI model, how is this different? We might have this use, so we do have this use conv variable. If we are using it, we call conv nd, which I don't know what conv nd is. Here's average pool nd. I don't see torch nn here yet. We do have torch nn imported. We have this attention pool 2D, which is, I guess we are copying from clip. And using a bunch of torch stuff, including, and we have this QKV attention thing, which I think that we've looked at. We looked at some QKV attention related thing. I don't know if there's this class or another one. And then the forward step looks different. We're reshaping a bunch of stuff similar to what we saw before and calling QKV projection. And I don't know how this is related to OpenAI yet, but we're calling interpolate here with, what is this, upsampling or downsampling? That's upsample. So somehow this is different. I don't know how to think about, I guess the thing that's OpenAI related is that we are using this clip model as a source of inspiration or source of code or something. I don't know how to think about what is, somebody told me what these, the computation graph. I don't know how to think about which building blocks should be in the computation graph, which trade-offs you're making, and how efficiency works, how gains and efficiency change over time. So the kind of the details of all of the implementations are pretty much totally lost on me at this stage. But at least the kind of what they are what the computations that they're modeling, I think they're starting to take shape a little bit for me. I was curious about this DPM solver, and I think I'm going to go after that. Forward SDE. I'm going to guess this is stochastic differential equation for a stable. No, I don't know. The forward SDE ensures that the condition distribution Q T given 0. I don't know what this LaTeX thing is. I think that's a literal bar. What do we have on the right hand side here? Here's some sigma t squared times I. Let's look up DPM solver. A fast ODE solver, diffusion probabilistic model, is a fast, dedicated higher order solver for diffusion ODEs with the convergence order guarantee. It's suitable for both discrete time and continuous time diffusion models without any further training. And then I guess we should figure out what a diffusion ODE is. I would think it would be a PDE. The diffusion equation. Yeah. It's well, at least the diffusion equation as I know it and as represented here as a partial differential equation. I don't know how they're thinking of the ODE. Solving the corresponding diffusion ordinary differential equation, blah, 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 blah. They have a semi-linear structure. They consist of a linear function of the data variable and a nonlinear function parameterized by neural network. And I'm not sure if SDE here is supposed to be stochastic. Yeah, stochastic differential equation. I don't know. Why ODE? I'm not sure. Maybe I think this is too mathy a paper for me to read it via Wallabag, but maybe I can print it out or something and read it later. And that, I think, is where I'm going to stop Stable Diffusion. We're at about 2.5 hours, which is much longer than I've been usually going on. This is the first time I think we looked at an implementation of a one of the big locally runnable AI things. I think that we've looked at other machine learning libraries like the XLA, linear algebra accelerator. I feel like this would have made more sense. First of all, if I were more familiar with PyTorch and the PyTorch.nn thing, unfortunately it seems like any machine learning project like this is going to depend on one of the big machine learning libraries, and if you don't have at least a little bit of a sense of what that library is doing, then we're kind of in the position of reverse engineering what the API is up to. So I think it would make sense for at some point in the future to look at a couple of the big machine learning libraries, and then there's a bunch of stuff that are like if you're in this field, then you're kind of expected to know at least a handful of different like network structures, tricks, and so forth that will show up, and why they are showing up. They might be for optimization, they might be for convergence, they might be for making sure that we don't get known bad artifacts that were common with previous solutions and so on. And that sort of knowledge, I'm not really sure the fastest way to pick that up. Like if you just start reading machine learning papers, you'll have essentially the same problem. And a lot of times, like a single machine learning paper will only cover one of those things. So it's really more about knowing a literature. And I think that perhaps for that sort of thing, it's okay if we just pick that up along the way. But it's a little bit hard to both not have the domain knowledge and also not know what the libraries are doing. And maybe it's a little bit easier to get a handle on the libraries, and pick the domain knowledge up as you go. So that's what I'm thinking. I think it would also be interesting to look at some of the UIs, because the UIs, like in this stable diffusion repo, we saw a couple of different samplers, but the UI should have code that has information about like when you would choose one sampler to versus another. Like when the settings are this way, then there's maybe some code path that chooses this sort of sampler, and so on. And that's another way I think to get information about all the different methods, is to look at a project that kind of unifies a bunch of those methods and makes them available with hopefully some sort of opinion about how that's supposed to work. So, the Carpathy is a great intro video. I'm sure he does. He's got a lot of great stuff. I'll see if he has anything recent about all of this stuff. At some point, and I've mentioned this on the Discord before, I'd like to look at some of the classic papers. We've discussed doing a reading group sort of thing. So we will do that at some point. But for now, that's all I got. I got to go. Have a good rest of your week. In the US, we're about to go on holiday, but I'll be back next week and I'll look at the original Satoshi Bitcoin code, or at least what claims to be the original Satoshi Bitcoin code. I don't know how to verify that it's actually the code he wrote, but that's what it claims. So thanks for watching. That's all.